It's his second lecture on molecules, clocks, and metrology. So take it away, Jun.
Okay, I hope you are enjoying the summer school very much, and I will start picking up where I left off last time, which is, I believe, was talking about molecular resonances. And before I start, let me ask if there are any leftover questions from last time, and we can go from there. If not, then I'll keep going. But do let me know if you need me to stop. So, okay, I'm sorry. I'm just trying to place the screen in the right place so I can see some of your faces. Okay, so as I was discussing last week, 2 days ago, when you apply electric field, you can start to deform the rotational ladder. And at a certain electrical field, you can find a place where the spacing between the ground rotational state and the first rotational excited state, and between the first rotational excited state and the second rotational excited state are matched. And this so-called degeneracy condition, that if you create a map of energies of two 1010 molecules and how that energy scales with electrical field, and when they come across into degeneracy with 00 plus 20 molecules, you have these energy crossing, and these energy crossing can be made avoided by the dipolar interactions. Therefore, if the two molecules prepared in the first rotationally excited state, 10, approach each other below the electrical field where the energy levels crossing with 00 plus 20, you can see that as you come up to this branch below the electrical field of resonance, because of the dipolar interactions, pushes energy barrier lower, meaning this 1010 molecules will have an easier time to reach that degeneracy to create 0020. Therefore, it will lead to a loss of molecules that was originally prepared at a 1010. So as you approach from electrical field that's below the resonance, you can imagine if there's a reaction loss, the reaction loss will be enhanced because the barrier is being pushed down. On the other hand, if the two molecules 1010 are coming down from electrical field, higher electrical field, then the field that's having a zero crossing have the degeneracy, then you can see the dipolar interaction raise the barrier up, as indicated by my laser pointer, then indicating there will be a barrier if the two molecules prepared the first rotational excited state approaching each other, they will actually be resisted by this resonance from approaching each other. And that leads to this picture of, this exactly now I'm plotting the adiabatic energies of these two 10 molecules as they approach each other as a function of the intermolecular distance. You can see that if you are coming from electrical field greater than the crossing point, you have this barrier, while if you're approaching from below the electrical field resonance, you have this attraction. Okay.
So Jun, there was a question on the chat of why are we interested in E2 and not E1 from Grace?
Oh, E1, E2, both are interesting. I'm just making one of those examples. They're actually very equivalent, and you will see experimental data-wise will tell you we'll see two resonances here. Sorry, I didn't make that clear. It's just an example, and the physics-wise, it's very similar. Okay, so now you see this consequence of this electrical field-induced resonance, and what we do in the measurements is indeed very dramatic effect. If you are approaching, you prepare two molecules in the first rotationally excited state, and if you place electrical field above that resonance, you can see these molecules live there for a long, long time. This is the density plotted as a function of time. These molecules live there for 10, 20 seconds. While if you prepare these molecules just below the resonance, the scale of the time where the molecule gets lost is extremely fast, it's very short. And in fact, the insert shows you over just a 20 millisecond or 40 millisecond, the molecules are being lost away.
Jun, there is also a question about what you mean by adiabaticity when you adiabatically prepare.
adiabatically prepare. Okay, that means the molecules, their velocity approaching this resonance is slower. The energy scale associated with the thermal energy is smaller than the gap of the opening dipolar interactions. So you're not jumping across this avoided crossing.
Can you remind which quantum numbers you're showing in these kits?
These are, okay, if we come back here, remember that rotational state quantum number is 0, 1, 2. These are rotational letters, J equals to 0, J equals to 1. But of course, there's a projection. Once you're in 0, you only have 0, 0. In 1, you can have 1, 0, and 1, 1, and 1 minus 1, and so on. These are the numbers I'm showing in the kits. Make sense?
Yes, thanks.
Okay, so this is a very dramatic effect. And in fact, what's really so interesting is this: we are changing the electric field by less than 0.1% or 0.1, 0.2%. And you can see this dramatic difference in the time scale of the reaction loss by 3 orders of magnitude. And so if you plot this as a function of the electric field, now one of the students were asking, why did you talk about E2 but not E1? You see 2 resonances. One is associated with E1, the other one is associated with E2, and they're very sharp resonances. And the sharpness of the resonance actually tells you exactly the ratio of the dipolar interaction energy versus the stock shift. The energy after all the molecular energy states are changing as a function of the electric field. And so if the changing is really fast as a function of the electric field, you will go through the resonance rather quickly, and it gives rise to this exceedingly sharp resonances. And actually, we were able to plot over a very large scale of electric field, varying from 0 kilovolts per centimeter all the way out to 15 kilovolts per centimeter. And you can see there's 2 resonances. And along the scale of from 0 to all the way to 11 or 12 kilovolts per centimeter, that scale of the reactive loss looks like as if it's a constant, but it's actually not a constant. Has all the structures of the dipolar interactions on the 2D plane, which I explained in the previous lecture. And what I want to draw your attention to is I can have these molecules standing perpendicular with respect to the plane or lying on the plane, when this is described as theta equals to 0 degree, theta equals to 90 degree. If I remind you of this configuration that I showed on Monday, remember we can show both configurations where the molecules are perpendicular to the plane or lying on the plane. In both cases, we were able to show this resonance actually works. And this is the 2 sets of curve, one in blue, one in red, indicating the resonance happening at the same location. And it really doesn't matter whether the molecules are approaching side by side or head to tail. This molecular resonance that's mediated by dipolar interactions happening, of course, at the same location, because the location is where the rotational resonance is being brought in by the electric field. So that's independent of the orientation. The dipolar interaction has some strength difference, and that can give rise to the structure being slightly different, but otherwise the resonance looks very much the same. The reason I'm spending this much time to tell you about this collisional resonance actually works for both orientations, when it's perpendicular or horizontal. It tells you that this resonance will allow us to not only working with molecules on 2D plane, but it can actually take these molecules out now to the 3D landscapes, and those resonances should still work. This relates to the question, I think it was Michael who asked on Monday, by going to 2D, you can avoid these molecular loss, and are you going to now forever stay in the 2D landscape? Well, the question is answered here, that if we can make this work, regardless of the molecular orientations, then we should be able to take this back to the 3D and still make this shielding resonance to work for you, even in 3D. So this is indeed what we recently did. Using this resonant electric field shielding, we can now liberate these molecules away out of the 2D trapping. We can put them back onto the 3D. And this is the theoretical plot done by John Bone and Guvan Comenir, our theory collaborators. showing that in 3D, you have this anisotropic landscape. But what's different from the first 3D landscape I showed you back when I was describing when you turn on electrical field, molecule will lead to loss. Here you can see there's always protective barriers around as long as electrical field is above the particular zero crossing point of the resonance, of rotational resonance. While if the electrical field is on the other side, below the zero crossing point, then you will see it's an attractive landscape where the cross section will tell you that loss will be dramatically enhanced. And so now we are doing this experiment in 3-dimensional tracks instead of in 2D tracks. And you can see the trapping frequency is much more comparable, only a factor of 5 difference rather than a factor of 1,000 difference. And you can indeed measure this the two-body loss coefficient beta as a function of the electrical field. And you can again see the two resonances, E1, E2, and you can see the differences of the reactive loss beta coefficient varies by almost 3 orders of magnitude as you tune across this electrical field in a very sharp resonance. And again, if you want to show this dramatic effect at the place where the loss is enhanced, the green curve shows the molecules are lost at 10, 20, 30 milliseconds. While if the molecules are protected by the resonance, the beta is very low. The molecules live there for 10 seconds, 15 seconds. So very dramatic, 3 orders of magnitude difference in 3-dimensional traps now. It's no longer 2D trap, but using this trick of resonant shielding. And that's a pretty...
How does this depend on the confinement? Does you have to do any dependence on the confinement in 3D, or do you?
No, it's actually no longer. Yeah, the confinement can be, so this really works. It's like just 3-dimensional space using resonance to shield it. And that's because we showed in 2D, you can have molecules coming head to tail or side by side. This shielding mechanism works for all situations. So that's actually quite interesting. The only question then you may want to ask is, well, what about elastic part of the dipole interaction? Now that you can finally got a 3-dimensional trap of molecules living there for a long time, and you can turn on dipole moment, you can shield away the loss. What about the elastic part of the dipole interaction? And that's something we want to demonstrate as well. So we again try this trick of the thermalization. Remember on Monday, last lecture, I talked about cross-dimensional thermalization in 2D. In the 2D case, we change the pancake in one transverse direction and look at the other transverse direction. In the 3D case, of course, you can shake in any other way you wanted. And in this particular case, we shake the pancake along the direction of where we apply the electrical field, or where the trapping frequency, remember, is like 200 hertz versus 40 hertz. So we shake the molecules along the slightly tighter confined direction, like this ellipsoid indicating. And then we apply electrical field at the position where you have the largest elastic or inelastic ratio. This is where the loss is being shielded and elastic collisional cross-section is still appreciable because you have an electrical dipole moment. And we can study this thermalization effect, and indicating like as we tilt the angle of the electrical field, in fact, you can actually see very dramatic differences in the thermalization. When I make the temperature, for example, in one axis to be much hotter than the other axis, thermalization would require these two different axes to thermalize, right? The temperature will approach each other. When the angle is perpendicular to along the direction of the more tightly confined direction, you can see thermalization is not so great. But when it's tilted 45 degree, the thermalization happening on a much shorter time scale. And if you study that across the entire angular dependence, you get a curve like this, which tells you, because this is dipolar interaction, it's anisotropic. It tells you at 45 degree, it turns out that's the best cross sections for thermalization compared to 0 degree or 90 degree. And this has been studied before by Francesca Foligno's group using magnetic dipole with atoms with a magnetic dipole. And she has shown similar dipolar anisotropy for thermalization. But now, for the first time, we can actually shield away the reactive loss of the molecules and demonstrate this. So we even can do evaporations in 3D instead of the 2D to do using this electrical dipole moment to induce the dipole-assisted evaporation. And that brings back to higher phase space density in 3D. So this really leads to many exciting explorations. I think that I can't emphasize enough, once you have a system that you can tune the elastic interactions while shielding away the inelastic interactions, finally this opens up a landscape where you can use molecules to do to explore a number of interesting many body physics, whether it's condensed matter related or just a pure AMO platform systems, some of which were outlined by John Bone, Anna Maria, and myself in this review article of Science that laid out some of the futuristic experiments. When we were writing this review 3 or 4 years ago, we had not realized that the fact that you can really shield away these losses and really bring up these elastic interactions. So 2 areas, for example, we are now actually already starting to work. One is in collaboration with Anna Maria Ray's group, since the molecules can be confined in 2-dimensional pancakes and their loss can be shielded away by either this resonance or by just simply using electrical field, large enough electric field to tune the molecules to be perpendicular with each other. And we are studying the coherence now already exceeding 1 millisecond. So this is actually getting to the point where you can study the correlations of the magnetic, well, I said a magnetic moment, but it's not, it's electrical dipole. But you can think of, electrical dipole as a 2-level system, as a magnetism as well. And you can study this dipolar physics with dipolar interactions to start to have a correlated collective effects of these rotational degrees of freedom of the molecules, which is, you can consider it as a spin squeezing of this rotational degrees of freedom. You can also, we have some preliminary data as well to study hydrodynamics of these molecules because they have long-range dipolar interaction mediating their collective behavior. You can actually study putting these molecules in an optical trap, and you excite them in the collective motion and how these molecules start to behave like liquid hydrodynamic modes. So all these are interesting areas, and I want to share with you one, and along the way, these experiments are actually ongoing. And especially for this collective spin squeezing experiments that we're preparing, one experiment we have been doing is to be able to select individual layers of molecules. So remember when I told you that we can load these molecules into these individual pancakes formed by this 1-dimensional optical lattice. We typically have about 2 to 4 or 5 layers of molecules occupied. And we do not have sufficient optical resolution to go inside and just individually using optical imaging resolution to see individually image of each pancakes. Plus, sometimes you want to image from top down, you want to image from this direction. And if you do that, all these pancakes are behind each other. So how do you really image a single pancake is a question. And so we came up with this trick. You can apply electric field, of course, to make the molecules oriented with respect to the plane of the 2D traps. At the same time, you can apply electric field gradient along this lattice, meaning that each lattice will experience a different electric field. As you already see from previous slide, as you tune the electric field, the rotational energy spacing is changing. That means that I can use radio frequency to address the rotational transition. If I remind you, going back a few slides, when I was talking about rotational resonance, remember I started with this particular slide. As you tune the electric field, this rotational state spacing is changing. So now if I have a gradient of the electric field across these pancakes, that means within each pancake, the molecules are going to respond to a particular electric field. And between neighboring pancakes, they're going to respond differently. And in fact, this is exactly what you see. as you tune the radio frequency, see pancake number 1, pancake number 2, pancake number 3. So this tells you can use one particular radio frequency to select only a single pancake, and then remove all other pancakes because they're in a different quantum state. You can use laser light to remove all other molecules. Therefore, I can select a single pancake. Or as you wish, I can give you 2 pancakes, 3 pancakes. So this gives you this opportunity to prepare bilayer systems, single layer, multiple layer systems with different rotational orientations. And that's quite exciting. These are the capabilities that we have wanted to have for a long, long time, to be able to have these single site. It's not a single site of a single molecule, but it's a single pancake, which is still a single site selection and imaging. And we can actually do coherent spectroscopy, that post-spin squeezing, now pushing this time scale over multiple milliseconds. And the one really fun experiment we just recently did is the interlayer spin exchange. And now imagine they have 2 layers of molecules, and I can prepare one layer of molecules to be at a 0-0 state in the ground. Another layer, for example, the molecules in the 1-0 state, so they have an opposite orientation, bilayer system. These 2 layers, these molecules have a dipolar interactions, right? So they can, in some sense, they can exchange their dipole, and that will lead to some interesting dynamics. We can also prepare layers with 2-0 molecules and so on. And just to remind you that there is a dipolar interaction between 0-0 and 1-0, or 1-0 and 2-0. However, if you prepare molecules of 0-0 and 2-0, there is no dipole moment, right? There's both same parity state, so there won't be any dipole moment. So we can use these different combinations of rotational state selections to set the background signal if there's dipolar interaction not turned on or turned on, and see the differences.
There's a question in the chat.
Yes.
It says, so Garrett, do you just want to ask?
Go ahead.
Sure. So I guess I was thinking about that layered pancake thing you were showing earlier, where you had the field. But if the pancakes had the same polarizability, you might say, then you wouldn't be able to distinguish them by the shift, right?
When you say the pancake has same polarizability, you're talking about the trapping frequency in the electrical field. Is that they are being trapped by optical trapping field, not by the electrical field, DC electrical field.
Mm.
Yes, the DC electrical field, these molecules are being confined by interference of the optical laser beams. Mm. And so indeed, there's a polarizability. These molecules, the reason they can be trapped is because they are polarizable under the laser light. And you're also correct. The polarizability can actually be tuned by you applying a DC electrical field. And so in our situation, the DC electrical field we apply modifies the polarizability slightly between these pancakes, but it's not enough to actually separate them. We actually apply, in addition to the DC electrical field, we apply DC electrical field gradient. And so there's minute changes on the polarizability in terms of the trapping frequency, but in terms of the dipolar interaction energy and so on, that certainly is affected because the DC field polarize them. The AC field do not actually polarize them; they just trap them.
So does the DC field and the AC field come from the same place?
The DC field is applied by the electrodes I described in the previous lecture. Remember, I showed you 6 electrodes. Do you remember that cell? Yeah, so the DC field is applied by, actually literally by power supplies that you DC power supplies that you apply current to it, while the AC field is applied by the laser beams. It's like a little tweezer, and you just heard from Antoine's talk, right? He used laser beams to manipulate atoms. He is using the polarizability of the laser. That's the AC field we're talking about. The AC field is at a frequency far, far higher than most of the molecular rotation or vibrational frequency. They are responding to the electronic degrees of freedom of the molecules to create the polarizability. But the DC field is actually really relating to lower frequency, like a rotational or lambda splitting, there's kind of degrees of freedom to polarize them.
I see.
Does that make sense?
Yes. I think 90% of that makes sense.
Okay, excellent. It's actually really interesting. When I was at your age and we're trying to understand how the polarizability, I mean, one can give a really interesting lecture about polarizability of atoms or molecules with a field. Because as a student, you say field is a field, or no, what's the difference? But you can see, you know, you tune the frequency from DC to radio frequency to microwave to terahertz to optical frequency. As you move along this frequency of your field, what you will see is you'll hit those resonances of individual degrees of freedom. Like the molecules can rotate, and then rotation happens in a microwave. So when the microwave frequency is below that rotation, you can consider that the field is DC. But when you go above the rotation, suddenly that field it reacts to the rotation in a different way with a phase shift. Like you're pushing a child on pendulum, right? You know, you will see that if you're pushing frequencies below or above the pendulum resonance frequency, the response is very different. There's a phase shift. And as you keep going to the higher frequencies, you hit a bunch of resonance. That's why your molecule is fascinating. You see this microwave resonance, you see terahertz resonance of vibrational states, you see electronic resonance. And every time you go through resonance, molecule responds to you in a complicated way. And you have to actually sum together all these states to really understand how molecules responding to the combination of those fields. So what I'm describing to you, hopefully, is making sense. But no, what we are doing now is in order to be able to manipulate a molecule, a complex object, we are pulling out all the tools out of the toolbox, whether it's a DC electrical field, whether it's AC electrical magnetic field. We are going to do whatever we need to manipulate the rotation, to manipulate the vibration, to confine them in optical traps, to use DC field to orient them. You know, all these fields have their own purpose to play, responding to a particular way that molecules respond to. You see what I'm saying?
Yes, that makes sense. Thank you.
Like even do a simple haircut, you know, a good stylist pulls out different size of scissors, and it just, you know, it's just a precision control of a particular object. I'm sorry for making that analogy because I just went to get a haircut to prepare for the summer school. That's why I experienced that precision metrology they experienced on my head.
Thank you.
Okay. So that makes sense.
Can I ask a question as well?
Yeah, please.
So you have the electric field gradient that you're applying across the pancakes to resolve the molecules that are in each layer. Presumably, though, you're also still working pretty close to that resonance to help suppress loss. Is the size of the electric field gradient significant enough that you see a big shift in like the loss rates between pancakes?
Excellent question. Actually, in this particular experiment, because it's in 2D, we went back to the 2D. The 2D, you are like a really nice region because you have two different ways to shield the loss. You can do this just by orienting the molecules perpendicular to the pancake. That, remember, already allows you to shield the loss.
Sure.
And at least it's not enhancing the loss when the dipoles are being induced. Or you can use resonant field. At this experiment, we are not using the resonant field. So the electric field is actually quite feeble here. We are using just about kilovolts per centimeter to orient them. And the loss is quite manageable at the time scales of hundreds of milliseconds.
Okay, thank you.
Okay, so we can prepare these states now with these individual pancakes, and it's actually the next effect that we will be collaborating with Anna Maria and among other theory friends is to explore whether there's a many body effect. Actually, we see some really interesting behavior yesterday, like when we study these spin exchanges. The energy scale, there's a single particle spin exchange interaction, which I will come back to that point. But because there are multiple molecules can do spin exchange simultaneously, there may be a many body enhanced spin exchange rate. And we are trying to see whether we can actually observe that in the experiment. But let me actually tell you like really quickly one experiment that we did, which is already can convince you this is interesting. You know, remember we can prepare pancakes in any kind of a combination now. So for example, I can put, you know, if you look at my laser pointer, I can prepare one pancake in the middle with n equals to 1 molecules and then nothing else, a single pancake. Or I can prepare 3 pancakes with the middle molecule in the n equals to 1, but the 2 surrounding layers to be 0, n equals to 0. or you can have the middle to be n equals to 2 and the surrounding layers to be n equals to 0. You can see the reason why I'm doing this is I want to have a spin environment where they can do either spin exchange because of dipolar interaction, or they cannot do spin exchange because there is no dipole interaction between 0 and 2. And therefore, I can actually study the loss. When the molecules, by spin exchange, the blue molecules came onto the red side because of a spin exchange, they can immediately be lost because these are S-wave particles. These are molecules which have different states. So the molecules themselves are not tunneling. I'm sorry, I should make that clearer. But the rotational excitation is changed. So you can see that initially I start with red and blue states. Some of the blue guys go to the red, some of the red guys go to the blue. And they, because of a spin exchange, it's not the guys are going there, but the excitation went there. And those excitations were considered as a very small minority in these blue or reds. I probably shouldn't be using blue-red states as an analogy. Again, that's not completely appropriate. But nevertheless, you can see the reason why when you have these spin exchange happening, because of the S-wave collisional loss is fairly large, they will immediately be, leads to a large loss rate. And this is what we observe. There are three situations, right? If you have no neighboring layers, where you have prepared in single pancakes, the loss rate is relatively small. If you prepare the neighboring layers to be in delta n equal to 2, meaning you have 0 molecules in the middle and 2 molecules on the side, or vice versa, the loss rate is also manageable, almost as if these other spin layers were not there. But as soon as you put neighboring layers to be on the opposite parity states, then you will see loss rate immediately goes up by a factor of 10. And that's really mediated by spin exchange because you have a dipolar interaction. So, and what we are exploring is we can actually tune the electrical field gradient and see whether we can see this gap, like how much electrical field gradient can suppress this. Once we actually tune the electrical field gradient after we selected individual molecules, we can then tune the electrical field gradient to any arbitrary values we wanted. And you can turn it off such that there is no gaps anymore, or you can leave on and tune it to different values with a gap. And you can actually study how the spin exchange gets inhibited by using different electrical field gradient. So you can see we are really taking advantage of electrical fields where you use them to polarize them, you use them to select individual pancakes. You can use this to tune the interaction energy or create gaps between the individual sites. So that leads to actually going a bit backwards in terms of the history. That this reminded me of an experiment we did earlier, where that was triggered by our theory friends, Alexei Goshkov. I think you're going to hear from his lecture later on in the summer school. But this work, I believe the collaborators was Anna Maria and Kaden. So the idea they laid out is to treat molecules as dipolar spins, where you have these molecules confined in this case a 3-dimensional optical lattice. And these are the rotational states I've been talking about, 0 and 1. You can think of it as spin down, spin up, and they can be connected by microwave. And if you apply DC electrical field, you can polarize them, right? All these bells and whistles are coming together to play a role. And I can put molecules individually in these 3-dimensional optical lattice if I have a very low entropy quantum system. And now you can actually write down a Hamiltonian to describe this quantum system. And you can see all of these spin interaction terms, the so-called, well, first of all, you have a geometrical factor, VDD. This is a dipole-dipole interaction, as we know from your undergraduate studies of electromagnetism. Dipolar interaction has this anisotropic factor 1 minus 3 cosine squared theta. That theta is the angle between dipole orientation and the vector connecting the two dipoles, and they divided by the distance raised to the power of 3. And then inside you have the so-called spin exchange interaction, where the two dipoles, if one is up, one's down, they can spin flip back and forth because of the dipolar interactions. You can also have the so-called, the spin exchange. There's the term, the spin Ising term, is actually when the two dipoles are just placing nearby, and there's a DC interactions between those. And that's the Ising term. And there's a spin exchange term when the dipoles are opposite orientation and they can have the exchange. With our typical optical lattice, this interaction energy is only order about 100 hertz because it's obviously dependent on the distance quite strongly and the dipole moment. You may have heard from Antoine's talk where we use Rydberg atoms, they can get to a much, much larger interaction energy. But 100 hertz, a few hundred hertz is quite excellent for us already. That's because these molecules in principle can live for tens of seconds. And so you can see the interaction energy is far beyond the lifetime or the coherence of the system can potentially have. And then this will be enough for you to see a lot of interesting dynamics there. Is there a question? No. Okay. So, so you can see that if I have a cheesy animations on the left here and this 3-dimensional plot, you can see like I have one dipole is being flipped. Remember, I can use electrical field to select individual site. And then of course, if I can do that with along one direction, I can do that in all 3 directions by using 3 different electrical field gradient. I can make one particular molecule feel so special that you can spin flip it with microwave without having to spatially resolving it. You're just using spectroscopy, energy landscape to resolve it. So you flip one molecule to be different from the rest. And you can actually study the spin exchange. As you can see this animation, these molecules are flipping their spins, right? And these are molecules are physically pinned down. The molecules are not moving around, but excitation, rotational excitation is moving around. And just imagine that I instead of having only one molecule being spin flipped, I have a line of molecules being spin flipped, or have a plane of molecules get spin flipped compared to the rest. That would be really interesting, sort of a many body localization or delocalization effects of transportation. So there's really interesting 3-dimensional Ising models, this full 3-dimensional Heisenberg picture that can be studied with the polar molecules. And actually, and as I said, we step backwards a bit in history. In fact, about 10 years ago, we did put these molecules in 3-dimensional optical lattice. It's just at that time, the molecules were still thermal, so the filling fraction is very tiny, and you can see like most of the sites are empty, but occasionally have molecules occupying there. And they indeed live very long. We can have 25 seconds coherent lifetime filling in these 3-dimensional optical lattice. And also a few years afterwards, after the first work, we actually did this so-called synthesis of molecular matter by creating a dual Mott and a band insulators. Essentially, BEC, you heard from Eric Cornell, you heard from Wolfgang Ketterle. You know, you create these Bose-Einstein condensate and a Fermi degenerate gas. You create as low entropy as you can. You load them into a 3-dimensional optical lattice, and if you do it just right, you can fill one particle per site, one rubidium particle per site, and one potassium particle per site, and you merge them such that rubidium, potassium, one each, on each site, and then you can merge them into a molecule. And
Jun,
that
there's a question. Sorry to interrupt.
Go ahead.
In the chat, there's a question in the chat. Yeah.
Yes, Leo, please.
How would you probe such a So the question is, how would you probe such a spin lattice system? You mentioned earlier that you could not image separately layers in one lattice.
Yeah. So when you say probe, we are talking about the 3-dimensional lattice. In 3-dimensional lattice, the probe would, you can either really preparing a higher numerical aperture lensing system to try to do individual site. In the summer school, you guys are going to hear about quantum gas microscope work. And we actually talked about this, thought about this, and have a paper written up in a proposal paper, how to do this kind of a spin resolved, lattice resolved, side-by-side probing of these individual molecules. The current experiments we are doing with layers, there we can already do individual pancake imaging because we can use electrical field to select individual pancakes.
I see. There's also a question from Storm.
But Jun, just to complement, even collective observables can provide important information. Yes, like Ramsey spectroscopy that we did for the 3D system before. So it doesn't need to have single site addressability to see interesting physics coming.
And yeah, I actually have a slide right after this, exactly touching on this point Anna Maria just made. There's also a readout from a macroscopic portion, which is looking at the ensemble average of spins, degrees of freedom, how that's evolving and so on. You can probe dynamics without resolving individual particles. Resolving individual particles is of course very powerful. It give you a very microscopic picture of what's going on. But you can also, you know, prepare your system in a microscopic way, but read out with the macroscopic observables. Leo, was there another question?
Yeah, there was another question from Storm. Storm, do you want to ask it?
Yeah, I just wanted to clarify that these spin flip excitations we're talking about now, those are different than the rotational modes we were just discussing, right?
The spin, okay. Actually, let's go back to this particular slide. You know, the spin in molecules really is a pseudo spin that's encoding the rotational degrees of freedom. So if you look at n equals to 0 and n equals to 1, you can consider 0 is spin down, 1 is spin up. You know, it's a spin half system up. You can, of course, say, well, there are many other rotational states that's available, but you can prepare their spin by microwave addressing. You can use this particular microwave photon, 2.23 gigahertz, to prepare coherent superposition only between 0 and 1. Therefore, give yourself a two-level system, and that's spin half, pseudo spin half.
So in this animation where you show the dipole flipping direction, that's not actually what's happening. Then it is
the dipole flipping direction is, you can think of like 0 goes to 1, 1 goes to 0. It is actually dipole flipping direction literally because 0 and 1, when you apply electric field, if the molecule stays at 0, the orientation of the molecule is actually opposite with the molecules which is staying at n equals to 1. And that's just because they have opposite parity and they actually respond to the electric field differently. One is so-called weak field seeking, the other one is strong field seeking. Like one is attracted to the electric field gradient, the other one is repelled by electric field gradient. And therefore their orientation actually literally flip. Does that make sense, Storm? Oh, you're still confused.
I'm still a little confused. Like if we were in like an L equals 1 state, I would expect that then the dipole would not have a defined direction because it'd be rotating along the rotation axis.
Well, actually, you're absolutely correct. This is actually the initial question of the very first lecture when we said, if the molecule is in only a single quantum state, there is no dipole moment. You're absolutely right. And thank you for actually being very good on this. But when you apply electric field, there is a state mixing. So those original quantum state that they solved with a molecular Hamiltonian without external fields. These 0, 1s are so-called good quantum numbers. They were good with respect to the Hamiltonian of the molecule. But when you apply electric field in the lab, you are mixing these quantum states. So this n equals to 1, strictly speaking, has turned into n prime, which has a slight mixing of the original majority of n equals to 1, depending on electric field strength. And a little bit of field of n equals to 0 gets mixed in. That is actually connected to how the dipole moment is being induced. It's all coming from, if you remember in quantum mechanics, when you have a Hamiltonian, you write down eigenvectors, eigenvalues, and you apply perturbations. The electric field you can think of as a perturbation. When you do that, there will be off-diagonal elements coming up due to that perturbation. The off-diagonal elements allow you to re-diagonalize the Hamiltonian that will give rise to modified eigenvalues and modified eigenvectors. The modified eigenvectors is the new quantum states under the combined effect of the original molecular Hamiltonian and applied external electric field. So this n equals to 1 is no longer strictly n equals to 1 in the bare molecular Hamiltonian. In fact, it has mixed n0, n1, even n equals to 2. So because of that, there is induced dipole moment that allows n equals to 1 to look as if it's going to spin down. And n equals to 0 itself is no longer a pure n is equals to 0 stated as well. It actually has little n equals to 1 character gets mixed in there. So when I say molecules in n equals to 0 state with applied electric field, what I really meant to say, it's in the modified new eigenvector of n equals to 0 state. Does that make sense now?
Yes. So these excited states, do they still have, like, angular momentum is no longer a good quantum number because we've broken the symmetry?
Yeah, that's correct. Yeah, yeah.
Still
Because you have this external electric field. Yeah, exactly.
Yes, just to complement, yeah, because just going to Jun's slide, if you see icing and exchange, that's exactly what Jun is mentioning, just to complement. So in icing, you have the up minus the down. These are going to be 0 if you don't have electric field. You need electric field there. But the one below that it says spin exchange, the up down a little bit below, then you can do it without the electric field when you have a superposition.
Yeah, excellent. Thank you. So like the fact that you write down, D up, D down. Sorry that didn't go through that. You could have caught me already at that point. You said you must be lying. You know, you told us in a single quantum state can have dipole moment, and here I'm writing down a D up, D down, and that's because this D is already coming from not a pure state, but rather a mixed state. The state mixture is dependent on the electric field strength with respect to the rotational spacing between the two opposite parity states. Okay, in the end, it's really like I always find that whenever a professor questions me about quantum mechanics, I just set up myself a 2x2 matrix. It's really easy. You have a 2-level system, you have an energy spacing between those, and the off-diagonal element is nothing but dipole moment of the matrix element multiplied by electric field, and you put this there. And you just re-diagonalize that 2x2 matrix. And I think anybody who has taken the first year quantum mechanics class would know how to do that. And that would gives you like a little exercise. You will feel really comfortable actually after you have done that, okay, this is where all the stock shift is coming from. This is where the dipole interaction is coming from. And this is where, different fields can come in to dress the molecules in different way. So I would suggest do a little quick exercise on these 2-level systems.
Yeah, and if you are lazy, I don't want to do it. Inspired by Jun, a long time ago, Kaden and I wrote a review where you really look at the physics, the derivation of the 2-level system. I can put the review in the chat so you can start looking for the 2-particle, and because this Hamiltonian there, as Jun exactly says, you can get it just from 2 atoms. So that.
Yeah, thank you. I think that will be really helpful. It gives you a connection to, I try to think about things in a very intuitive way, but when you write down mathematics in a couple of lines, it really does summarize things in a very nice form, in a very compact form, and allow you to really make all the connections there. Okay, if I move on a little bit, let's see, where were I? Yeah, where was I? I was talking about you can make it it's a really interesting system where you have a 3-dimensional optical lattice and you put 1 atom of each species in each individual site, and then you make molecules. Using this technique, we were able to do a 25% filling about 5 years ago. But now we haven't gone back to the 3D lattice, but we can do much better than this now because we have a degenerate quantum gas compared to at the time, the T of TF was still only 1.3 or 1.4. Now we can have a 0.3, so we can redo this 3-dimensional lattice experiment. And all of this is connected to this spin exchange that we have recently done between the lattice pancakes. It's actually interesting, different platforms to study these effects. But in the 3D is interesting is because that spin exchange does not lead to loss, unlike the loss that I showed you in the pancakes, because there you have a multiple molecules in each pancake. So when the minority goes into a red excitation goes to the blue place, it gets collided with the blue molecules and it gets lost. But when you have only individual molecules in each lattice site, you can have a spin exchange going on. There won't have any real chemical loss. It's all of this is happening sort of in elastic ways, right? So that's why 3-dimensional optical lattice is quite interesting. maybe the final point to just reinforce what Anna Maria said, that you can read out these kind of spin dynamics without even having individual readout capabilities. Now, suppose you have a lattice that prepared with a spin down, and so spin down meaning the molecules in the rotationally ground state, and you can apply a microwave, prepare them into a coherent superposition between ground and excited state. Again, you can say spin up and spin down. In that case, then if you wait for a while, there will be spin exchange between the neighboring molecules, because each molecule is actually in coherent superposition of both up and down. And nevertheless, they can spin exchange and make them actually, these two molecules become entangled. We would have to do disentanglement. You have heard about quantum entanglement. This is exactly quantum entanglement type of experiments you can perform. And in fact, Antoine, he has been doing some really interesting experiment using Rydberg atoms to entangle two neighboring atoms in the neighboring tweezers. And you can see now the connections, right? Whether it's tweezer experiments, whether it's the molecular dipole moments, they are really deep down, you write down these Hamiltonians, they're the same thing. And so instead of microscopically read out individual spins, we can just wait a little bit and probe the overall spin coherence of the entire macroscopic quantum system. And so this shows so-called Ramsey contrast, the fringe, how much, you put the molecules in coherent superposition. If we have a single molecule, then it should be tumbling back and forth of a long coherence time. But if we have lots of molecules interacting and they're spin exchanging, and you can see this contrast actually decays away. The more molecules you put it in there, the faster the decaying away. But this decaying away of the contrast is not because the molecule is being lost. The physical molecules are completely intact. It's their spin degrees freedom is being entangled, being scrambled, and so on. And that's why the single particle readout with the Ramsey contrast goes away. But you can do actually sophisticated multi-pulse readout techniques. I don't need to tell you the technical details of which, but it's just the spirit that indeed you can use particular observables and actually look at how the Hamiltonian drive the system dynamics and construct different ways of probing with spectroscopy techniques to read this dynamics out. So now that we have, this is the work that we did a while ago, and you can see Caden at the time was still in Colorado, and we wrote this, he first authored this paper about really figuring out the many-body dipole interaction, the three-dimensional optical lattice. At that time, the lattice filling was low. Also, we did not have actually DC electrical field. This was the first generation of experiments. We only had a microwave at that time, and there's no DC electrical field. Well, now we have everything. So we can actually turn on the so-called JZ, the Ising interaction, because we can apply DC electric field. And we can, of course, still have the spin exchange interaction. And if you look at the spin exchange versus Ising interactions as a function of electric field on the top right corner of the plot, you can actually see that places by the time you go to 6 or 7 kilovolts per centimeter of DC electrical field, the interaction will flip the relative strength. So it's a really interesting area where you can actually start to see the phase transitions by exploring the different ratios of J perpendicular over JZ, the spin exchange strengths versus the Ising interactions. You can study the transport localization effects I mentioned to you earlier in 3 dimensions with the 1 over R cube interactions. It's a classical computer untractable problems. That's where the quantum simulation experiments like this will play a particular strength here. You can, of course, also implement exotic lattice geometries, which we don't have particular immediate experimental platforms to do it, but those will be long-term interest areas for us to get into, or many groups now working on molecules will probably get into that. And there's other interesting areas like spin orbital coupling and Floquet dressing, spin squeezing, all those effects that we'll be looking into. So with that, I want to end my molecule part of the discussion, thanking the group, Kyle, Will, and actually Cal. They are the 3 graduate students, Jun Lu, Luigi, and Giacomo are 3 postdoc, but unfortunately, Luigi and Giacomo have both left us. Fortunately for them, but But over the last couple of years, this team really has made a lot of advances preparing the molecules in both 2D, 3D, quantum degenerate, 10-ion interactions, overcome inelastic loss, and so on. And I also want to thank all the theory collaborators, John Bohm, Guan Creminaire, on dipolar collisions, Anna Maria Ray on spin squeezing, lattice spin models, dating back more than a decade of interactions with Eugene Daimler and Svetlana Kozaczykova on the coherence, polarizability, and so on. So I'm going to end my molecule talk here. If you have questions, we can stay here for a little while, and then if time permits, I'm going to give you the second lecture, which is the optical atomic clocks. Thank you. Do you have questions here? I'm going to stop sharing and let's see.
So if
So while
you
the students
could
think of
speak up.
questions, okay. Can I ask a question? This is my first time hearing about these layers and your spin exchange between the layers. So can you see coherent oscillations there, or do the losses just prevent this? You just lose atoms, and so you see the losses and you're done. Or is that?
Yeah, Kaden, actually, it's a really interesting thing that I'm going to, if I may, I might share a whiteboard with you. You can see this, yeah, Kaden. So like what it's describing, there's two pancakes and the molecules are like this. And the way we are seeing is spin exchange allow you to have, this molecule to spin exchange such that this turns into top and this molecule turns into down, and they have reactions there. What we are studying now is looking at this rate, this beta rate as a function of the electric field gradient, delta E. So if you apply, this is under E1 and this is E2, and the difference E2 minus E1, of course, equals to the gradient delta E multiplied by the distance L. So by tuning delta E, what we are doing is making E2 and E1 to be very different. If E2, E1 equals to 0, what we see is that the loss, for example, is particularly strong. But as we tune the electric field, what we see is that this loss comes down. And eventually, you can understand, eventually when delta E is large enough, that these two dipoles are no longer in resonance. They can no longer spin exchange. And what we are seeing is really interesting, like this width is something on the order of a kilohertz, which is actually much larger than, remember we said 100 hertz was a spin exchange of a single particle. But we don't have enough data yet. People actually working in the lab, and Kyle and Will and so on. It would be really interesting to zoom in, like they have some weird data in the middle where there's like maybe a very sharp needle, and there could be a single particle physics, but the data is too noisy and it's only 1 day old, so it's not appropriate to really share or talk about it. I think once we have more data, we'll probably knock on your door to ask for help if we think of things that we cannot explain. Yeah. But that's what your coherent oscillation would be like. Could you actually go in there and zoom in? Like here, what I'm plotting is sort of a landscape of delta E. But of course, once you figured this out, you could imagine going there and actually watch, do time-dependent sequence of it and look at the 0 and the 1 population. What's interesting is we can, with the field gradient, we can actually read out both populations simultaneously. You can do actually molecular system galaxy experiment, or we can actually hold the molecules staying in n equals to 2. That's a very stable place, and then read out one spin state at a time. Looks like somebody is drawing a picture.
Just, sorry, let me comment briefly, Kaden. So the interesting part and the excited part is that it's imagine that you have two big spins, spin 1 and spin 2. There can be exchange excitations between one, but in principle, if they were some population spin excitation between 2 and spin excitation between 1 and 2. And what Jun is controlling is this energy difference between the two for the exchange process between the spin. So it's a pair production process when you go here and you start to produce, you start to produce molecules here. and it's controlled by the linear part of the gradient because it's going to change the difference. But also there is a term that is non-linear here from the exchange interactions when it start to happen between 1 and 2. So it is, as Jun said, there is a tuning knob that is single particle, but is also a tuning knob that is coming from the exchange interactions themselves. So it's going to be kind of, you can see a pair production process between two. I mean, imagine that there were not losses at the moment. What you have is you are going to start to a spin product. I mean, you have, these are the seeds, and at some point you are going to have molecules here down, molecules here up. These are the pair production process that you generate, and you can really control by the energy splitting between the two states. So this resonant, the electric field that Jun is saying is going to control actually this energy, the tuning, that you can start to flip-flop. But in addition, there is this nonlinear process within each pancakes that also is going to provide an additional energy balance to the resonant process. So it can be quite exciting.
So
There's
I
also
have
a
many
question
questions,
by
but I think Grace has a question, so maybe.
yeah, Grace is. Go ahead, Grace.
Oh, I was just wondering, so like we just heard from Antoine about like the stuff he's been doing with optical tweezers with Rydberg atoms, and I was just like wondering, when you're working with molecules that are not in like highly excited states, are there certain advantages to this optical lattice platform, or is it like, are there things that you can do with an optical lattice that you couldn't be doing with tweezers, say?
Right. No, there are questions which was actually Kaden yesterday was asking that similar question, like comparing different platforms. There's a magnetic dipole of atoms. There is Rydberg atoms. Rydberg atoms have much stronger dipole moment, right? And but you go to Rydberg state, however, it's very short-lived. And another interesting area is if you prepare coherent state between Rydberg state and a say ground state, those guaranteed so far has been very difficult to say matching the optical polarizability so that you can actually keep the molecule or atom still be trapped. While in the molecule case, for example, if I create 0 and 1 coherent superposition, I can actually, like a clock, which I'm about to tell you, the so-called magic wavelength trap, where both states can share the same trapping potential, meaning you can actually create coherent superposition between 0 and 1 that's supporting the dipole moment, and yet they are long-lived. They are not dissipating away. They have a long coherence, and so this is the area where, in the end, it really doesn't matter. It's like if you borrow from quantum information processing a terminology called circuit depth. It's all about within the coherence time, how many operations can you make? Meaning it's always a ratio of interaction energy over dissipation rate. And so whoever gets that longest time, because in the end, we are doing simulations anyway. I can never really realize in my molecular system with a feeble 100 Hertz interaction to really simulate in realistic way a condensed matter system that can have energies on many gigahertz. But what I can do, however, is my coherence time can be 10 orders of magnitude longer than condensed matter system. So in the end, my interaction energy versus coherence time still allow me to do a lot of interesting physics that could be very much the same as what's going on in a real condensed matter system. Just everything is scaled up by certain factors. And I see that as a relationship between Rydberg atom and a polar molecule, the similar way. I do think the Rydberg experiments super interesting, that especially with tweezer, you can individually program it. And there is one technical challenge. If you're using Rydberg states, how do you keep that in as part of your coherent system, or you just always use it as a knob to allow you to entangle? So in lots of the Rydberg experiments, people are just sort of, whenever you're doing the Rydberg operations, you actually turn the trap off, right? The atoms and molecules are actually in free flight. While the molecule experiment, you are doing it in the native landscape of the lattice. I'm sure there are other, as you dig into each individual experiment, there's always interesting specifics that you have to study and control. But whether if one can start to realistically build a three-dimensional system with low entropy and start to really be able to unravel the full three spin half Hamiltonians, I do think that system would be second to none.
I want to also mention, Jun, that molecules offer the possibility to have, maybe, well, there are other possibilities in Rydberg, but with the nuclear spins, there is an additional knob that you can control that can be very long-lived, and there are other experiments that start to also study the intercombination of rotational and nuclear spins that is very exciting of molecules in the future, perhaps.
Yeah, maybe actually one interesting comment to make on science, really on AMO science is, in the end, people are thinking exactly the same thing now. In the strontium ytterbium tweezer experiments, they can also use this nuclear spin, which I'm going to talk about as well in the clocks. So what is really interesting when you ask questions like this, Grace, what's triggering or inspiring is the whole field learning from each other. Or I'm learning from Rydberg atoms, and I'm sure Rydberg atoms initially was inspired by the work done on the magnetic atoms or molecules, and it's just vice versa, right? So this is making each platform to implement the advantages of the other platform that we can follow in, and it's yet still maintain its unique advantage. So this kind of a cross comparison is very healthy. And the nuclear spin, well, molecules also have all these rotational states I even haven't talked about. And Caden has written a paper, or at least has seen his proposal. You have an infinite synthetic dimension lying up there that we haven't taken advantage of. There's infinite possibilities to explore. Some people even proposing like this infinite rotational ladder allow you to study itself boundary problems where, in the middle of the rotational states versus in the bottom of the rotational state, there's a boundary there, and you can study this many body localization of the rotational states. I think the possibility is endless. And to me, this tells you, that's why I love to be experimentalist. Once you get a one quantum system under control, there will be a lot of interesting capabilities open up, and our great theory friends will always find interesting new opportunities for us. That maybe is more interesting than the technical details I was telling you in terms of the summer school spirit.
Do you want to go ahead then and start sharing the second?
Okay. Should I? I was waiting for the director to give me the command.
Yeah, I think it's useful. I mean, it's still 15 minutes left, so I mean, as much as we can use all your information, all the great things that you're going to tell us, Jun, the best for us.
Yeah, but so Jun, how much time do you think you'll need?
I think 1 hour would be perfect. Actually, I don't need a 1 hour. Right now we have looks like I have 45 minutes left. Is that correct?
No.
No.
We have 15 minutes.
15 minutes.
How many? 15?
Yeah, 15. So maybe we can create an extra lecture if you think it's more. So one option is you take that 15 minutes and that's it. Or, another option is we stop here, let students relax before the poster session, and we could create another lecture for you to, more fully cover what you wanted to cover. That will be an hour long. So that's what we could do.
Leo, don't ask me what I want to do. I think, and I'm at your service. I think we should ask what students want. Indeed, maybe it's good to take a vacation, not vacation, take a break.
Yeah. I suggest to take a vacation because, as Jun said,
4 votes for extra lecture, 5, 6, 7, 8 votes for extra lectures. So
let's do an extra lecture because this way students can relax for 15 minutes. For you to try to cram in, where you think is an hour of material into 15 minutes would be useless anyway. So we can, if you're available this month and you can tell us what your constraints are, we can work you into the schedule where, on a lighter day.
Yeah, sounds good. I also don't want to have students hate me that to create another lecture for them, another burden on their already tight schedules.
No, I think the lectures are wonderful. It's just we want to do the most pragmatic thing, and I think we already had a pretty heavy load this morning. So I think it's nice to just take a break and for students to relax a little bit, get their lunch ready, and then reconvene on Gather Town for poster session.
Sounds good.
Does that sound good? So why don't we do that?
Yeah.
Okay, everybody.
Thank you.
Well, unless there are more questions, so we can take more questions. Well, potentially more questions. If not, then we'll.
I really enjoyed this. This is one of the most interactive summer school. I've taught a couple of summer schools already this summer, and this is a very nice way of. Students are very active. I enjoyed that.
Yeah, big thumbs up to all the students. So thank you, students, for really embracing this and really participating. Thank you.
Well, at the risk of holding people hostage, well, I guess anyone can leave, but I guess I was going to ask another maybe slightly more technical question, which was what you think the biggest limitation with molecules is at the moment, and where the most improvement can be made to help advance ultracold molecules in general.
Well, the biggest obstacle of the molecules is just it's really hard experiment.
Yeah.
That's being like the biggest limitation, honestly. Before we solved this loss problem, of course, that was the biggest limitation. The molecule, we can create the molecules, they always get lost. But that seems to be now finally solved. I think that some of you already asked, is it possible to continue to advance the state of the art? And indeed, if you get this 3-dimensional crystal working and you got all these, I want to see individual molecules moving around. It'll be fantastic, right? So how do you put all these? We already put all these electrodes jammed into that vacuum system. Can we put a really high resolution? We got a now 1 micron resolution lensing systems in there. Not quite enough to individually resolving, but enough to resolve with electric field gradient. I just think it's just a multiple of those technical, and remember earlier, somebody was asking, I forgot his name for a second. Anyway, that was asking about the field, the polarizability, and so, no, Garrett, right? That was Garrett. Yeah, so Garrett was asking that question. And so you have to apply all these different field control, microwave, IF, DC. You have to make sure that imaging is really good. You have all these optical beams going in. So it's just a technical complexity, I think. Sure. I do think at this point, scientifically, if we can lower the entropy a little bit more, getting T over TF to be let's say less than 0.1. The number of possibilities that we laid out in the science review, I think we can just tackle them one by one. And I've been talking to a number of really fantastic theory colleagues in condensed matter, like Raul Nakashon. I don't know if you guys hear his lectures, but he has lots of ideas of dipolar molecules as well. And you can put molecules in the cigar, turning them, there's just endless possibility. Like we in our department, Leo has worked with Noah Clark, who is a true pioneer of liquid crystal. And you can't help start to think about, well, of these different pancakes, I can start to think about these link up these pancakes. Almost like liquid. It's a liquid, but it's also crystal. So there must be a connection there. And also think out loud. People are very excited by the bilayer system, but we can actually do bilayer, trilayer, quadrilayer. So if more control capability gets implemented into our system, being able to read out, I do think it's very interesting. There are a lot of other people now thinking about using molecules to do quantum information processing. We are not quite yet jumping on that bandwagon, to go on to make gates. Right. Although you could. But I feel, like Grace was asking, there's different platforms have different possibilities. I want to see like a really compelling reason why the gates with molecules is really much better than Rydberg and so on. Then maybe we can entertain those. But right now, even just on the condensed matter many body physics without quantum information connection, there's a lot of interesting experiments one can do.
Sure. Thank you.
Some of you
Okay,
should
so what do we?
just molecules.
Why don't we break and then we'll see you all in Gather Town in about 15 minutes or so.
Thank you, Jun. Thank you
Okay,
very much.
yeah, of
Thank
course.
you, June.
Bye
Yeah,
bye.
thanks. Of course, they're interested in molecules. I think they're building molecule experiments, right, Michael and Garrett? It's,